Good evening. It's my pleasure to extend a very warm welcome to one and all to this lecture series on the history of mathematics being organized by the Mathematical Sciences Institute Belagavi. Well, the initiative that we started with speakers who gave these talks earlier include Professor Ravi Kulkarni of Bhaskaracharya Pratishtana, Pune, Professor S.G. Dani, formerly of TIFR Mumbai, School of Mathematics, and Professor C.S. Rajan, again from School of Mathematics, TIFR Mumbai. The objective was, as you all know, that what is true of an individual is true of an institution or for knowledge for the reader. Then we thought that we should look into the past, how the history has recorded these knowledges. In particular, for a mathematical community like us, we are interested in the history of mathematics. When we extended invitations to these experts, we had specific inquisitions to them that they can pick up any frame of time in the history and then present to the audience. That has been the spirit of our objective, and that's how these speakers presented their talks. It was not pandemic then, it was an offline. The scholars came to Belgaum, Professor Rajan and Professor Dani, they came to Belgaum and delivered these lectures. But whereas Professor Ravi Kulkarni did this in Bengaluru in association with Jaina University, where Raman is a faculty there. So we had the first inaugural talk under this lecture series of history of mathematics at Bengaluru. Indeed, this year we have also decided to celebrate at our institute as mathematics for women in mathematics. So under this theme, we wanted to invite this time a woman mathematician. We were just looking at. So when we contacted Professor Sharada of TIFR Mumbai, then she suggested me that my daughter Ambika Natarajan, today's speaker, would fit the bill. If you don't mind, why don't you extend this invitation to her? So by accident, we have here with amidst us Ambika. It's nice to see you, Ambika, and I extend a very warm welcome to you. And on behalf of our institute and on behalf of all my mathematical community, I extend a very warm welcome to you. And I make a brief introduction about Ambika because this must inspire the youngsters. Ambika has a very impressive academic credentials. She has 2 masters, one in English from IGNO, then she has a master's in biotechnology. Then she went on to earn her PhD in the history of science. She switched over to history of science. She was fascinated by this field of area when she was doing her master's in biotechnology at US in Michigan. That's what she was exchanging her experiences. A while ago I spoke to her. What made her to switch over to this history of science and philosophy, where she has done a lot of her work. So, without taking much of your time, let me also put on records her stint in teaching and the position she held. Presently, she is a visiting professor at Center for Excellence in Basic Sciences, University of Mumbai. She was instructor of history, School of History at Oregon State University, Portland. She traveled under Austrian Cultural Forum, and she holds memberships to many professional bodies. Some notable ones include coordinating Council for Women in History, member of American Historical Association, German Study Association, and many more. Indeed, it's a great pleasure for me to present Ambika, a right person, a historian, to tell us about how mathematics, the history of mathematics as a historian of science to present to this audience. Ambika, you are most welcome, and I hand over microphone to you.
Thank you. That was very charming introduction. Thank you so much. It's such a pleasure to be here. I just want to confirm two things before I start, which is, can you hear me and can you see me?
Yes.
Yes, we are able to hear you. You are visible also.
Okay, mathematics in ancient India raises many problems for a historian. The primary problem is that the subject is shrouded by two extreme worldviews, both of which not only lack historical accuracy, but do not subscribe to any consistent and rigorous historical methodology. The first worldview is expressed by those scholars who wish to claim that there was no real mathematics done in ancient India before the arrival of Christianity around 500 CE. This is the Eurocentric vision that arises during the colonial period and still holds some ground today, mostly outside select circles of experts in the field of history. This vision is expressed by Paul Tannery, who, when he learned from Islamic sources that Indians were the first to use the sign function, devoted himself to finding out possible ways in which they could have acquired this knowledge from the Greeks. For Tannery, the very fact that Indians knew of sign function and used it for astronomical calculations was enough to convince him that they must have got it from the Greeks. This tunnel vision towards the accomplishments of Indian civilization, and indeed all other non-Western civilizations, comes from the inability to accept that there might have been great achievements in other civilizations that is comparable to the achievement of ancient Greece, from whom the West claims to have inherited all its artistic and scientific accomplishments. I changed my slide, you can see?
Yep.
Yes.
Yes, great, thank you so much. Another person who dedicated his life to showing the derivative nature of Indian mathematics was a person by the name of G.R.K., who is still quoted as an authority on Indian mathematics. Kay was prepared to neglect the weight of evidence to the contrary and insisted that the Bakshali manuscript was written and copied from an earlier text dating to the Christian era. Again, Islamic sources unanimously attributed the origin of present-day numerals to India, and neglecting the overwhelming evidence in all these sources, Kay pressed his project. This tunnel vision is not confined to mathematics. The accuracy of information on the preparation of alkalis contained in the Indian textbook on medicine, Sushruta Samhita, dating back to several centuries before BCE, stunned M. Berthelot. He then sought to prove that this had occurred after India had come into contact with European chemistry. The distortions that resulted from the work of Kay and others has been taken seriously by many people. Despite the refutation of such findings by reams of scholarly works authored by historians and experts in the field who have emerged in the past 2 decades, many people outside the field remain immune and continue to propagate these distorted Eurocentric myths. And these myths are represented as well-established fact. While on the one hand you have Eurocentric tunnel vision of this kind, the second group of scholars comprise of those who wish to claim that all mathematics originated from ancient India. This is the Indocentric vision that arises from a noble yet somewhat overzealous desire to rehabilitate Indian accomplishments preceding the colonial era. This tendency, more than anything, keeps us trapped in an endless tug of war with the Eurocentric vision, and in doing so leads us to give credibility to this narrow vision of the world that we seek to discredit in the first place. So I wish to draw inspiration from scholars who have sought to rehabilitate the uniqueness of Indian mathematics through rigorous historical analysis. I'm going to name a few among a rapidly growing group of scholars and historians who have, for the past 2 decades, entered this field with increasing determination and have rejected both Euro and Indo-centric visions through their commitment to historical accuracy and their application of rigorous historical methodology. These include George Geragis Joseph, David Nelson, Julian Williams, J.A. Banks, R.S. Bishop, M. Frankenstein, C.C. Gayton, and the list continues to grow. These scholars have argued that Indian mathematics and non-Western mathematics in general was not only original and grand in its heyday, but also that it contributed to and in turn benefited from interactions with Near Eastern, Chinese, and Islamic cultures, and more recently from its contact with the West. This presentation draws inspiration and much of its content from George Joseph's body of work. Historians classify the development of mathematics in India into 6 periods. All of you can see this map where I have circled India?
Yep.
Yes.
Yes, okay. The first period, between 3000 to 1500 BCE, coincides with the Indus Valley civilization. This is the period when we see scaled weights and measures and the development of brick technology that would have a profound influence on subsequent civilizations that developed in India. The second period, between 1500 to 500 BCE, is predominated by the arrival of the Aryans and the development of texts we know as Vedas, Upanishads, Code of Manu, etc. From this period, we have mathematical texts such as the Vedangas and the Sulba Sutras, and the elucidation of problems in astronomy, arithmetical operations, and Vedic geometry. Key mathematicians of this period were Baudhayana, Apastamba, and Katyayana. The third period between 1500 to 200 BCE coincides with the establishment of Indian states, the rise of Buddhism and Jainism, contacts with Persia, reign of Chandragupta Maurya and Ashoka, and the spread of Buddhism abroad. Vedic mathematics continues during this era, but it declines with the end of ritual sacrifices. However, Jaina mathematics becomes influential and number theory, permutations and combinations, the binomial theorem, and astronomical problems are developed. The fourth period, from 200 BCE to 400 CE has the backdrop of the Kushan dynasty, the Pandyas, Bactrian Persian, and the pervasive influence of Buddhism. In the fourth period, we see Jaina mathematics at its best. The rules of mathematical operations, the decimal place notation, the first use of the number 0, algebra including simple, simultaneous, and quadratic equations, square roots, details of how to represent unknown quantities, and negative signs are developed to great detail. The fifth period, from 400 to 1200 CE, is comprised of the imperial Guptas, rising to their heights under Harshavardhana, the flowering of Indian civilization in science, philosophy, medicine, logic, grammar, and literature. This is known as the classical period of Indian mathematics, when the most well-known works emerge. Key among them are the Bhakshali manuscript, Aryabhatiya, Panchasiddhantika, Aryabhatya Bhasya, Mahabhaskariya, Brahmasputa Siddhanta, Pati Ganita, Ganita Sara Samgraha, Ganitilika, Leelavati, and Bija Ganita. And there are several notable mathematicians in this era: Aryabhatta I, Varaha Mihira, Bhaskara I, Brahmagupta, Sridhara, Mahavira, and Bhaskaracharya, who is also known as Bhaskara II. The final period from 1200 to 1600 CE coincides with early Islamic dynasties, the birth of Sikhism, and the Vijayanagara kingdom in the south. This is the period when mathematics and learning decline somewhat in the north, but in the south there is rise of the Kerala school of astronomy and mathematics, and there is considerable work done on infinite series and analysis. The key mathematicians in this time period are Narayana, Madhava, and Neelakantha. Later, after Akbar ascends the throne of the Mughal Empire, many important works of mathematics are translated and expanded upon by the scholars in the Mughal court. Now that we have this overview, I'll now introduce you to some of the key characteristics and achievements of each period. The earliest evidence of Indian mathematics is found among the ruins of the Indus Valley civilization that goes back to about 3000 BCE, but we can perhaps extend it even further behind. Over 15 different sizes of bricks are found at Harappa, and the standard ratio of the three dimensions, length, breadth, and thickness, is always 4:2:1. Even today, this is considered optimal ratio for efficient bonding. Bricks of different sizes from Indus Valley sites were found to have dimensions that were integral multiples of the graduations of their respective scales. Apparent relationship between brick-making technology and metrology was to reappear about 1500 years later during the Vedic period in the construction of sacrificial altars of brick. The Aryans who arrived in India around 1500 BCE were pastoral people speaking a language that for a long time remained spoken rather than written. This language, Sanskrit, developed over a period of time to become a suitable medium for religious, scientific, and philosophical discourse. Its potential for scientific use was greatly enhanced by the systematization of its grammar by Panini. An indirect consequence of Panini's efforts to increase the linguistic facility of Sanskrit soon became apparent in the character of scientific and mathematical literature. This may be brought out by comparing the grammar of Sanskrit with the geometry of Euclid. The geometry of Euclid's elements starts with a few definitions, axioms, and postulates, and then proceeds to build up an imposing structure of closely interlinked theorems, each of which is in and of itself logically coherent and complete. In a similar fashion, Panini began his study of Sanskrit by taking about 1700 basic building blocks, some general concepts, vowels and consonants and so on, and proceeded to group them into various classes. With these rules and some appropriate suffixes and prefixes, he constructed compound words by a process not similar to the way one specifies a function in modern mathematics. Consequently, the linguistic facility of the language came to be reflected in the character of mathematical literature and reasoning in India. It may even be argued that the algebraic character of ancient Indian mathematics is a byproduct of the well-established linguistic tradition of representing numbers by words. Vedic literature went through 4 stages of development: the Samhitas, the Brahmanas, the Aranyakas, and the Upanishads. From what must have been a vast corpus of such writings, 4 great collections come down to us by the name of Rig Veda, Samaveda, Yajur Veda, and Atharva Veda. The Brahmanas, the second division of Vedic literature, are practical handbooks for those conducting sacrifices. Of these, an important source of early mathematics is Satapatha Brahmana. This contains one of the earliest mentions of the technical aspects of altar constructions. As an example of mathematics used in altar construction, I'm going to cite here Mahavedi. An altar called the Great Altar or Mahavedi was to be constructed for a ceremony. This altar was laid out as an isosceles trapezium with a basis of 24, 30, and 36 units each. Inside the Mahavedi, another altar had to be constructed in the shape of a falcon with curved wings. As you can see, the construction required copious knowledge of geometric shapes. Another important source is provided by the appendices to the main Vedas known as Vedangas. These are composed in the form of sutras, a peculiar form of writing that aims at utmost brevity and often uses a poetic style to capture an argument or a mathematical result. This form of writing was adopted by many scientific schools of thought that were flourishing in the Indian subcontinent. The Kalpa Sutras is the most important source of Vedic mathematical knowledge. This text contained literature on the construction and measurement of sacrificial altars, and this part of the text came to be known as Sulba Sutras. The Sulba Sutras provided instruction for 2 main types of rituals, one for worship at home and one for communal worship. Square and circular altars were sufficient for household rituals, while more elaborate altars, whose shapes were combinations of rectangles, triangles, and trapeziums, were required for public worship. The need to maintain equivalence of areas among the altars of various shapes raised a number of geometrical problems, the solutions of which led to early Indian geometry. 3 of the more mathematically important Sulba Sutras were the ones recorded by Baudhayana, Apastambha, and Katyayana. Baudhayana's work offers instructions to those conducting the sacrifices as to how to construct and chords. Instructions are statements of the Pythagorean theorem. The geometry of the Sulba Sutras grew out of a need to ensure strict confirmation of the orientation, shape, and areas of the altars to the prescriptions laid down in the Vedic scriptures. Such accuracy was just as important for the efficacy of the ritual as the meticulous pronunciation of Vedic chants. A remarkable achievement of Vedic mathematics is the discovery of a procedure for evaluating square roots to a high degree of accuracy. The problem originally arose from an attempt to construct a square altar twice the area of a given square altar. The geometry embodied in the Sulba Sutras is the outcome of a long and sophisticated tradition of brick technology inherited from the Indus Valley civilization. Therefore, as George Joseph argues, the chronology of Indian mathematics is filled with the help of bricks. There is a view that Indian mathematics originated in the service of religion. The proponents of this view have sought their main source in the Sulba Sutras. They argue that the needs of religion have determined not only the character of Indian social and political institutions, but also the development of scientific knowledge. Astronomy developed to help determine auspicious day and hour for performing sacrifices. The 36 verses attributed to one Lagadha, known as the Vedanga Jyotisha, give procedures for calculating the time and position of the sun and moon in various nakshatras. Also, a strong reason in Vedic India for the study of phonetics and grammar was to ensure perfect accuracy in pronouncing every syllable in a prayer or sacrificial chant. And the construction of the altars and the location of sacred fires had to conform to clear instructions about their shapes and areas if they were to be effective instruments of sacrifice. Public altars, like a falcon just about to take flight, allegedly would enable the soul of the supplicant to be conveyed by the falcon straight to heaven upon offering a sacrifice on such an altar. Then there are proponents of the view that the development of mathematics was largely secular. These people argue that the instructions given in the Sulba Sutras were mainly for the benefits of craftsmen laying out and building altars. Jaina, Apasthampa and Katyayana were not just scribes, but probably also priest craftsmen performing a multitude of tasks, including constructing sacrificial altars and maintaining fires and instructing worshippers on appropriate choices for altars and so on. The rituals associated with the construction of fire altars may simply be technological. In other words, Sulba Sutras may primarily be manuals for technicians. It doesn't matter which side of the aisle you fall. The point here is that whether it was developed for religious or secular purposes, Vedic mathematics, especially Vedic geometry, was quite sophisticated. Indian civilization has been consistently fascinated with numbers. In the Ramayana, for instance, Ravana commanded an army whose total equaled 10 raised to 12 plus 10 raised to 5 plus 36 into 10 raised to 4. Facing them was the rival army of Ram that had 10 raised to 10 plus 10 raised to 14 plus 10 raised to 20 plus 10 raised to 24 plus 10 raised to 30 plus 10 raised to 34 plus 10 raised to 40 plus 10 raised to 44 plus 10 raised to 52 plus 10 raised to 57 plus 5 men. Though fantastic, the numbers reveal the ease with which Vedic Indians used large numbers. Compared with the Greeks, who had no words for numbers above 10 raised to 4, Vedic Indians had no problems working with large numbers. Not only large numbers, but also very, very small numbers fascinated Indian mathematicians. Mesopotamian and Greek culture developed a full positional value number system on the base of 60, but did not use 0 as a number. The Greeks, who were intellectual inheritors of Egyptian mathematics and science, emphasized geometry to the exclusion of everything else. They were not interested in perfecting their number notation system. They simply had no use for 0. Further, they were not interested in arithmetic at all. Why? The Greeks claimed that arithmetic should only be taught in democracies, for it dealt with relations of equality. On the other hand, geometry was the study for case, for it demonstrated the proportions within inequality. Now, this might come as a surprise to some of you, as Greek is usually considered the birthplace for democracy. However, just because the Greek city-state of Athens tried out democracy, it did not mean they liked the idea. In fact, the Greeks were intensely suspicious of the system and intensely suspicious of the idea of equality, and therefore intended democracy only as a temporary solution to some political problems they were having. So they had every reason to reject the study of arithmetic, which they considered to be the study of politics, and that was in turn the study of democracy, which they did not want. In India, zero as a concept probably predated zero as a number by hundreds of years. The Sanskrit word for zero, shunya, meant void or empty. The word is probably derived from shuna, which is the past principle of svi, which means to grow. In one of the early Vedas, the Rig Veda, there is another meaning, the sense of lack or deficiency. It is possible that the two different words were fused to give shunya a single sense of absence or emptiness with the potential for growth. Hence, the derivative shunyata, described by the Buddhist doctrine of emptiness, being the spiritual practice of emptying the mind of all impressions. This was a course of action prescribed in a wide range of creative endeavors. For example, the practice of shunyata is recommended in writing poetry, composing a piece of music, producing a painting, or in any activity that comes out of a mind of an artist. An architect was advised in the traditional manuals of architecture, the Sulba Sutras, that designing a building involved the organization of empty space. For it is not the walls that make a building, but the empty spaces created by the walls. The whole process of creation is vividly described in the following verse from a tantric Buddhist text. First, the realization of the void. Second, the seed in which all is concentrated. Third, the physical manifestation. And fourth, one should implant the syllable. By 800 BCE, Vedic mathematics gradually declined with the rise of two great religions, Jainism and Buddhism. This period also saw the establishment of the first great empire in Indian history, the Mauryan Empire. The rise of Buddhism and Jainism around the middle of the first millennium BCE was in part a reaction to the excesses of Vedic religious and social practices. The resulting decline in Vedic sacrifices meant that occasions for constructing altars requiring practical skills and geometric knowledge reduced. There was also a gradual change in the perception of the role of mathematics. It became an abstract discipline for its own sake. The Jaina contribution to this change is extremely important. The Jaina school that rose to prominence in this period did some notable work in abstract mathematics. They were particularly fascinated with large numbers, which was intimately tied up with their philosophy of time and space. The mathematical correspondence was soon established. Just as emptiness of space is a necessary condition for the appearance of any object, the number 0, being no number at all, is the condition for the existence of all numbers. The attraction to operations with zero has endured in Indian mathematics. Both Bhaskaracharya in 1114 CE and Srinivasa Ramanujan of the 19th century appreciated zero. In an elementary class that Ramanujan attended, the teacher was explaining the concept of division through examples. Between 3 children, each child would get 1 banana if there were 3 bananas. Similarly, the share would be 1 banana if 4 bananas were shared among 4 children, 5 bananas among 5 children, and so on and so on and so on. When the teacher generalized this idea of sharing X bananas among X boys, Ramanujan asked whether if X equals 0, each child would then get one banana. There is no record of the teacher's reply. Ramanujan explained later to his school friends that 0 could be anything, since the 0 of the denominators may be any number of times the 0 of the numerators. The level of numeracy in traditional Indian society was high because of the lack of any institutional or philosophical inhibitions to the acquisition or practice of numeracy. The Jains had an interest in enumeration of very large numbers, which was intimately tied up with their philosophy of time and space. The Jaina cosmology involved 2 suns, 2 moons, and 2 sets of stars. One of the 4 sacred subjects of investigation for Jains was Ganita Anuyoga, inquiry into calculation. It was part of this inquiry that Jains developed interest in the concept of infinity and the infinitesimal. The most notable Jaina contribution was to the measurement of circles. In Jaina cosmology, the Earth is a large circular island called the Jambu Island, with a diameter of 100,000 yojanas. While there are a number of estimates of the circumference of this island, an interesting estimate mentioned in both the Anuyugma Dvara Sutra and the Trilokasara is 316,227 yojana. This result is consistent with taking a circumference to be given by square root 10d, where d is equal to 100,000 yojana. The choice of square root of 10 is the number we call pi, and this was quite convenient since Jaina cosmology, islands and oceans always had diameters measured in powers of 10. In 1881, near a village called Bhakshali, near the northwest border of India, a farmer digging in a ruined stone enclosure came across a manuscript written in an old form of Sanskrit. The Bhakshali manuscript is a handbook of rules and illustrative examples together with their solutions. It is devoted mainly to arithmetic and algebra. The state of Indian mathematics at the middle of the first millennium CE, as represented by this manuscript, can be summarized as follows. Mathematics of the classical period was practical and secular, being applied to everyday problems. Examples of profit and loss, computation of average impurities of gold, of wages, of gifts to be paid to subordinates, and of speeds and distances to be covered form the subject matter of the Bhakshali manuscript. The great interest in indeterminate analysis expressed in the Bhakshali manuscript reached an advanced level during the classical period of Indian mathematics. There is evidence of a well-developed place value number system that included 0. The ease with which this system is used in the manuscript suggests that the system predates the document by a few hundred years. In the middle of the first millennium CE, channels of communication within India where mathematical work was concentrated in 3 centers of learning, namely Kusumpura, Ujjain and Mysore, opened up. As did the communication between other cultures, first Persia, then Islamic world, then China opened up. The scene was set for the transmission of Indian mathematical ideas to the West and the incorporation of important Babylonian and Hellenistic ideas, mainly from Alexandria, Egypt. Aryabhatiya, the great work of Aryabhatta I, was composed in Kusumpura, which is present-day Patna, the capital of the Gupta Empire and an important center for learning. This work is a short and concise systematization of the knowledge contained in older astronomical manuscripts called the Siddhantas. Aryabhatiya contains the details of an alphabet numeral system of notation, rules of arithmetical operations, and methods of solving simple and quadratic equations and indeterminate equations of the first degree. The book pays special attention to trigonometry and introduces sine and versine functions. Two astronomers who followed Aryabhatta extended his work. They were Varaha Mihira, who constructed trigonometric tables. Hello? Something matter?
No.
No, it's just some disturbance.
Okay, sorry.
No, continue. Some sound was there. Continue.
Two astronomers who followed Aryabhatta extended his work. They were Varaha Mihira, who constructed trigonometric tables, and Bhaskara I, who would influence the mathematicians of the classical period as well as the Kerala mathematicians. The latter's notable contribution to mathematics includes his solution of indeterminate equations of the first degree and a remarkably accurate approximation formula for calculating the sine of an acute angle without the use of a table. Brahmagupta, the best-known mathematician of the Ujjain school, wrote comprehensive astronomy texts. He holds a special place in the history of mathematics as it was partly through the translation of his works that the Islamic world and then the West became aware of Indian mathematics and astronomy. Sridhara was the author of an influential Trisatika, and this work would hold sway as the most popular textbook of arithmetic before the composition of Bhaskaracharya's Leelavati. Mahavira was a mathematician from the mathematical school at Mysore, and his book, Ganita Sara Sangraha, was widely used in South India and influenced the development of mathematics in that region. Bhaskaracharya came from a family of court scholars in Maharashtra and wrote his famous Leelavati, which is a highly influential work in Indian mathematics. I'm sorry I couldn't get a better map of Bhaskaracharya's place that is estimated. Little is known about his life. In 1587, on the instructions of the Mughal Emperor Akbar, the court scholar Fizi translated Leelavati into Persian. And it was Fizi who told the tale of Bhaskaracharya writing this work in the name of his daughter. Bhaskaracharya's Bijaganita contains problems on determining unknown quantities, evaluating surds, and solving simple and quadratic equations, and some general rules in dealing with the solution of indeterminate equations of the second degree and even equations of the third and fourth degree. His cyclic method for solving indeterminate equations was rediscovered in the West by William Bruckner in 1657 CE. Bhaskaracharya won such great reputation that his manuscripts were still being copied and commented upon as late as the 19th century. The works of Mahavira, Bhaskaracharya and others contain some fascinating problems. Let me take one example here. Out of a certain number of sarasa birds, 1/4 the number are moving about among the lotus plants. 1/9 together with 1/4 as well as 7 times the square root of the total number of birds are found on a hill nearby. 56 birds remain on the Vakula trees. What is the total number of birds? This is from Mahavira's Ganita Sara Sangraha. So the solution to this problem is, if x is the total number of birds, this gives the equation x is equal to x by 4 plus x by 9 plus x by 4 plus 7 square root x plus 56. When solved, this gives the answer 576 birds.
Dr. Ambika,
Yeah,
could you take some questions in between, or you would like to answer at the end?
at the end.
Okay. Okay.
Okay. Another example from Mahavira's Ganita Sara Sangraha, which I will leave to the audience to solve, is 3 merchants find a purse lying on a road. One of them says, if I keep this purse, I shall be twice as rich as both of you together. "Give me the purse and I shall be thrice as rich," says the second, while the third exclaims, "I shall be much better off than either of you if I keep the purse. I shall become 5 times as rich." How much money is there in the purse? How much money has each merchant? Okay. It is generally believed that mathematics in India came to a halt after Bhaskaracharya. This is a myth, as we see luminaries like Narayana Pandit and Madhava of Sangramagama and Nilakanta Somayaji rising to prominence in India and the south during the Mughal period. The myth has evolved from the assumption that modern calculus developed from ideas and techniques inspired by ancient Greece. However, it is now established knowledge among historians that the origin of the analysis and derivations of infinite series, notably those relating to arctangent, sine, cosine, are not found in Europe. They originate in India. The six texts that constitute the main evidence of work of the Kerala school are Aryabhatya Bhasya, Tantra Samgraha, Yukti Bhasa, Kriya Kamakari, Karana Paddhati, and Sadratnamala. An important feature of these texts is that they are inspired by the ideas of Madhava of Sangamagrama. His fame rests on his discovery of the infinite series for circular and trigonometric functions, notably the Gregory series for arctangent, the Leibniz series for pi, and the Newton power series for sine and cosine. So how did some of this mathematical knowledge from India pass to the West? It has to do with the year 622 CE. In that year, Prophet Muhammad fled from Mecca to Medina. He had incurred the wrath of pilgrims who had come to worship at the shrine called Kaaba. The Prophet was preaching a monotheistic faith. 8 years later, he returned with an army of supporters. 2 years later, he passed away, but he had created a revolution in that part of the world. A few years after his passing, Islamic rule was established over areas stretching from North Africa to southern borders of France to the borders of China and India. Such a rapid spread was possible for two reasons. First, there was an egalitarian character to early Islam that was lacking previously in the region. Second, in many of the areas, the local rulers were so cruel and unpopular that the new Islamic rulers were welcome. After the early caliphs, the Abbasids came to power and would inaugurate in the Islamic world a scientific revolution of sorts. Baghdad soon became the capital of this scientific enterprise. For the next 200 years, Islamic scholars traveled all throughout the ancient world, collecting great works of science from Greece, Persia, China, India, and brought them to Baghdad, where they were translated and improved upon, then quickly disseminated through the Hajj pathway to India and China, where incredible work was being done. The arrival of the Islamic scientist Al-Biruni in India in 1018 CE as a prisoner of the invading army of Muhammad Ghaznavi was another important landmark. During his stay in India, he learned the language and culture of the country. Al-Biruni translated from Arabic into Sanskrit Euclid's Elements, Ptolemy's Almagest, and his own work on the construction of the astrolabe. None of these Sanskrit translations exist today. However, Al-Biruni's example was followed by Sultan Firoz Tughlaq, who occupied the throne of Delhi from 1321 to 1388. He ordered many Indian astronomical and mathematical texts to be translated to Persian. The Greco-Persian tradition of mathematics soon entered the Indian traditions of mathematics and inspired much of the later work done during and after the British era. Greek, Indian, Chinese thought were compiled, improved upon, and spread rapidly through the ancient world through the Islamic civilization, and soon landed in the western shores. And of course, we know the story of the Italian Renaissance and the emergence of the modern West. Now let me use the final few moments of this talk to tell you exactly what aspects of Indian mathematics landed up in the West. I emphasize that some of this is based on circumstantial evidence, Others have been proven to have originated from India, and still others have been rediscovered much later after Western scientists worked out these problems independently. I don't have sufficient expertise in the field of mathematics to confirm which is which, but here is a broad overview. So, first, the method of construction of 24 sign values, which was solved by Aryabhatta in 499 CE, was used by Regiomontanus in 1533 CE. The radian measure, Aryabhatta 499 CE, was used by European mathematicians 19th century CE. Square and cube root extraction, Aryabhatta 499 CE, Islamic mathematicians in the 10th century. Method in algebra including summation and finite series, Aryabhatta 499 CE, used by Islamic mathematicians in the 10th century. Methods in algebra including summation and finite series, Aryabhatta 499 CE, used by Italian mathematicians, specifically Bombelli in the 16th century. Number system with 0 as number and as positional symbol, used by Indians in the 6th century CE, was used by the father of algebra, Al-Khwarizmi, in the 9th century. Generalized arithmetic of fractions, used by Bhaskara in 600 CE, later used by Islamic mathematicians in the 9th century. Prime factorizing methods involving differences of squares, used by Narayana in 1356 CE, used later by Fermat in 17th century. Arithmetic involving 0, Brahmagupta, 7th century CE, used later by Arab mathematicians in the 9th century and European mathematicians in the 13th century. Elements of calculus, including derivatives of sine and cosine, by Bhaskara II in 12th century CE, used later by Renaissance mathematicians in 17th and 18th century. Continued fraction formulas, Bhaskara again in 12th century CE, used by John Wallis in 1655 CE. A proof of the Pythagoras theorem, Bhaskara II in 12th century, John Wallis again in 1655. Pell's equation, Brahmagupta in 7th century CE and Bhaskara in 12th century. Later we find it in Fermat challenge problem of the 17th century, which was solved by Euler in the 18th century. Infinite series for pi, an infinite series of sine and cosine, was used first by Madhva in 15th century CE, developed, and then later used by Leibniz, James Gregory, and Newton in the 17th century. Okay. So finally, I want to conclude with a few remarks. India has one of the most prestigious mathematical histories in the world. However, much of this history has been clouded by first Eurocentric visions and subsequently the reactionary Indocentric vision. And these distortions continue to be propagated. The field has recently attracted tremendous interest from many historians of science. Their efforts have gone a long way in restoring and reviving this legacy, yet there is a long way to go in undercutting the distorted influence of some earlier works such as those of Tannery, Kay and Berthelot. Above all, I wish to express through this lecture that there is a universality to mathematics that transcends cultures, and no one culture or region of the world can claim monopoly of discoveries and innovations in this beautiful subject. The sophistication of this subject has been possible through the collaboration of thousands of brilliant mathematicians all around the world, and the distortion of this history does a great service to all these brilliant minds. Thank you.
May I request Raman to propose vote of thanks? Raman?
Sure. Yeah. Am I audible?
Yes.
It's my great pleasure to thank the speaker of this session, Dr. Ambika Natarajan, for that splendid talk and mostly non-partisan view of how mathematics evolved, especially through the Eastern world. I would also like to thank the distinguished mathematicians who attended this lecture and supported this cause, like Professor Bushnurmat, Professor S.G. Dani, Professor N. Sarda, Professor Ellen Katkar, and many more. Last but not the least, I would also like to thank all the participants for having spared their time to listen to such lecture at the time when kind of humanities and history is not that respected. So In spite of that, we did get a good response. I thank all the active participants. And last but not the least, I also would like to thank the volunteers of MSIB for all the cooperation. Thank you, one and all.
Thank you very much. Okay, we keep this.
Thank you. Very great pleasure.